Hello, my name is Dragan Koch, and this is my presentation on gravitational wave detection for my class Introduction to Quantum Mechanics Physics 285. With that being said, let's get started. First, we will address what gravitational waves even are. Then we will talk a little bit about why we care about them. Then we will address how they work, and finally we will conclude with next steps and future applications. So I hear you ask, what even are gravitational waves? Well, gravitational waves are ripples in the fabric of space-time, created by accelerating massive objects like black holes. These distortions travel through space at the speed of light and were first predicted by Einstein's theory of general relativity. Before getting into how we detect these gravitational waves, let's talk about why they matter. These waves are incredibly difficult to detect and only show up when something huge happens in the universe. So it's fair to ask, why go through all of this trouble? Well, gravitational waves don't have much use in our daily life right now, and they probably won't in the future either. But in astrophysics, they're extremely valuable. They let us detect massive cosmic events like black hole collisions or signals from the early universe. They also give us a totally different lens through which we can view our world, one that doesn't rely on light. And this is of critical importance, because light can be easily distorted, for example, by gas, dust, or other objects in space. And since most of what we know about our universe comes from observing light, this imposes a huge limitation on us. Black holes are actually a perfect example of this. They don't let light escape, so we can't see what happens inside or what happens when they collide. But gravitational waves aren't blocked the way that light is. They pass through everything, carrying information straight to us. That makes them a powerful way to study events that we'd otherwise miss. Now that we understand a little bit about why gravitational waves are important to us, let's talk about how we can actually detect them. Gravitational waves were first detected on September 14, 2015 by LIGO, which stands for Laser Interferometer Gravitational Wave Observatory. LIGO is the largest observatory of its kind, made up of two identical detectors placed 3,000 kilometers apart from one another. Each detector has two arms that form an L shape, and each arm is approximately 4 kilometers long. Inside, there is a laser, mirrors, a beam splitter, and a light detector, all in vacuum. This setup works a lot like a Mach-Zehnder interferometer, where we overlap two light beams and study how they interfere based on their wave patterns. More specifically, here's how it works. A laser sends out a photon that hits the beam splitter. The splitter sends half the beam down one arm and the other half down the other arm. The beams are reflected off mirrors and come back. If the arms are the same exact length, the waves cancel out and they don't produce any light. However, if, for example, a gravitational wave passes through, then what we observe is a tiny flicker of light because the arms aren't quite the same length anymore. And this change is astronomically small, about 10,000 times smaller than the width of a proton. Now then, let's get into the fun stuff, which is the math. Gravitational waves generate a differential arm oscillation. This oscillation is spacetime stretching along one direction and compressing in the perpendicular direction, so as a gravitational wave is passing, LIGO's arms change by this tiny disturbance in opposing ways. This distortion in space is equivalent to a phase shift factor of phi, similar to the Mach-Zehnder interferometer. Therefore, the output state of the photon in LIGO with the presence of a gravitational wave can be described as a matrix with a phase shifter factor e to the I phi. To determine phi, we first calculate the probability of detector 1 and 2 using the Born rule, which we can also see here. And also we note that these calculations are the exact same, or almost identical, to what we did in homework 1 question 3. We can then solve for phi by subtracting the two probabilities and rearranging the equation. This gives us inverse cos p2 minus p1. Furthermore, for n number of experiments, the counts in detector 1 and 2 are defined as n1 and n2. We can then estimate the probabilities of p1 and p2, yielding us a more practical form to calculate the phase shift. Phi equals our cos of n2 minus n1 over n. Now that we know how to calculate the phase shift, we have to address that there are countless sources of vibrations on Earth, and billion times larger at that. How can we determine whether or not such impossibly small perturbations actually belong to gravitational waves? LIGO's detectors are incredibly sensitive, not just to gravitational waves, but also to vibrations of any kind, like for example, cars driving by, or earthquakes, or even slight temperature changes. To deal with this, LIGO uses two identical detectors 3,000 kilometers apart, and this distance helps in three major ways. There are local vibrations, like for example trucks, which get filtered out. Gravitational waves travel at the speed of light, so real signals will detect in both detectors only about 10 milliseconds apart. Having two detectors helps us figure out which direction the wave actually came from. When both detectors pick up the same signal at nearly the same time, computers can compare them, cancel out any differences, and isolate the real gravitational wave, which is how we can be sure. In the future, we may be able to use millisecond pulsars, incredibly stable, fast-spinning neutron stars, to detect weak gravitational waves. This idea goes way back to 1974, when G.S. Downes suggested that pulsars could be used for space navigation, though the accuracy at the time was off by about 1500 kilometers. By 1981, using X-ray pulsars, that was improved to 150 kilometers. Today we use millisecond pulsars, neutron stars that spin thousands of times per second. These stars are so consistent that they act like neutral cosmic clocks. And because of that precision, even small timing changes caused by gravitational waves passing through can be measured. Using these pulsars, we could one day navigate across the entire solar system with GPS-like accuracy. Small shifts in pulsar timing, called timing residuals, can reveal gravitational waves. But we have to filter out the known effects first. Shapiro delay is how gravity slightly slows down the signal. Einstein delay includes time dilation and gravitational redshift, basically how time and space warp. Glitches are random and can change the pulsar spin rate or behavior. When you subtract all of these known effects, the leftover signal may be from a gravitational wave. These pulsar timing arrays detect low frequency waves, things that LIGO can't pick up. With AI and massive data processing, we'll likely see these systems go live soon, thanks to tools like FAST in China or Mikrat in South Africa. Now then, here's a fun question for you to see if you've been paying attention. Why is the math for a Mach-Zehnder interferometer with a phase shifter equivalent to a gravitational wave detector? I'll give you a quick second to think about it and pause the video if you want to. Well, because in both systems you're measuring a phase shift caused by a change in path length. In the case of a Mach-Zehnder interferometer, it's a physical shift induced by a phase shifter which is physically placed into the Mach-Zehnder interferometer. However, in the case of a gravitational wave detector, that change in path length is the physical distortion of space itself as a cause of the gravitational wave passing through our system. Finally, we conclude with a list of sources that were used to make this presentation possible, and we thank you sincerely for watching.